So today class we move on and look at a couple more algorithms. We try to take a view that somewhat shows the analogy and differences with respect to what we've been doing so far. So we try to use least squares as kind of the seed of the various developments you're going to see. And in some sense, the last class about going from linear to nonlinear model, we're going to somewhat use that kind of systematically. So we're mostly going to work with linear models, and I'm just going to say, oh, you can do the same trick as we did last time and use features or kernels. Now, today we're going to discuss a logistic regression and supervector machines, which presumably you have all seen before. I guess the new gist is that we are going to, logistic regression is going to be pretty standard, and maybe we just introduce the representer theorem, which is slightly different. And it's going to be our excuse to present supervector machines exactly in the same way. Okay, so the presentation of supervector machines is quite different from what you usually see, and hopefully is simpler and is somewhat throw away some of the details that are usually used. And essentially, it's also an excuse to introduce the notion of subgradients, so technical tools from convex optimization and convex analysis, which is the generalization of the notion of derivative to functions that are convex but not smooth. Okay, it turns out that you can still do something. There is an operation called subgradient that plays the same role. So that's kind of the dual purpose of the class today. A fresh view on SVM using this new technical tool. So this doesn't work. And and if you wish, is also an excuse to look a bit more into classification problems. So far, we mostly look at the square loss, and now we would like to look at loss function, other loss function than the square loss, and particularly we're going to look at a loss function in classification. As if you remember, I think in my first class, we discussed the fact that while in regression, the difference is the meaningful quantity. In classification is the product that becomes the meaningful quantity. Because when it's positive, it means that your f has the same sign of y. If it's negative, it means that they disagree. So the sign of the product is an indication of whether your prediction is correct or not. I don't know if you remember, but we also see that least squares can actually be put in this format. And so, to some extent, you can use least squares also for classification problem. But today we focus on two other loss functions. One is the logistic loss that takes this form. And the other one is the hinge loss, which takes this form, where this is the maximum between 1 minus yfx and 0. Okay? So in drawings, I want to do like this. If this is the 0, 1 loss, and here you put the product y of x, the hinge loss look roughly like this. So it's flat here. It has a non-differentiability point here. And then it goes up linearly, and it's an upper bound on the 0, 1 loss. The logistic is looks like a kind of a smoothed version of this. It goes up similarly here, but actually it's never 0. Okay, so it's just asymptote towards 0 when yfx goes to infinity. Okay. So we would like to understand a bit. What these things are doing, and mostly look at the computation involved in computing the corresponding solutions. And we are going to look primarily at a regularized version of this. So we're going to consider x to be Rd and f of x to be linear. And then again, I'm going to point out where and how you can go from these to feature or kernels. Okay, but we mostly deal with the linear case because it makes the whole thing more elementary. And then we look at problems and estimator that are defined just by the empirical risk minimization on loss function like the one above that has this form for linear models. And then we consider this, where lambda, again, is a parameter that is bigger or equal than 0. Okay? So this is the kind of model we want to consider. And the minimization is unconstrained, is over all possible vector. And I'm going to call, as we did last time, this guy w hat lambda. Okay? So we're going to, as I said, we're going to spend most of our time understanding how to solve this problem for different loss functions. Okay? But I want to spend just a couple of words mentioning, without proving, a couple of results that somewhat allow to draw a parallel between what we discussed for least squares and this classification case. Specifically, if you remember, when we did least squares, we draw a parallel between this approach and the limit for lambda going to 0. You remember what that was? When lambda goes to 0, we obtain, depending on whether we are over-parameterized or not, either a least square solution or the minimal norm least square solution, which was given by the pseudo-inverse. Okay? So the important bit here is that it was the minimal norm solution among the one compatible to the data, meaning the one that satisfies an inequality constraint. Okay? Or just one, okay, if there is nothing else. So the question we want to ask, if there is some kind of analogous result for classification to this one. If I take the limit of this going to 0, where do I go? Do I go to something that is of a similar flavor to what we got? Okay? And it turns out that the answer is yes. And this is kind of a couple of extra slides in the note that I did this year, because it turns out that a bunch of works that have been studying neural networks and generalization of neural networks actually went back exactly to this property here and try essentially to generalize them from linear models to nonlinear model in the sense of nonlinear model in the W's. You remember last time I told you can, roughly speaking, make this nonlinear either by adding a nonlinearity here, and then it's nonlinear in the sense of a nonlinear function, but it's linear in terms of parameterization. And this gives you for free that you can essentially derive a lot of results from the linear case, okay? And that's what we do for a while. But the other situation, which is trickier, is the one where you add the nonlinearity outside. So now you trap the parameterization inside the nonlinearity, and this now it becomes a more complicated problem, particularly become a non-convex problem. So just the pointer here to future lecture is that the results I'm going to describe now recently have been extended to things like this, specifically to things where there is a nice, what is called an homogeneity property, meaning that you can, in linear model, you can scale up this, okay, by multiplying by a number. And here the idea is that you have a similar property here. Okay? That's just a side remark. So if you look at things like an absolute value of a ReLU, you have a nonlinear function that you can scale up in a kind of nice way. If this is just a positive number. Okay? Yes?
Using these other losses than square loss corresponds to like
This and the loss are separate, completely separate. You can combine them in any possible way.
So right now you're focusing on using different losses then.
Right, so my comment was just, I'm going to write down now a couple of results that remind you what is the limit of this for lambda going to 0, okay? And one of the reasons we are doing this is because these results are becoming, I think because it's interesting, okay? But also because analogous consideration has been recently done, not for linear models, but for nonlinear models in the sense of neural networks. And specifically, nonlinear models in the sense of neural network use something like a ReLU activation function, or if you want an absolute value-like thing. Okay? Of course. I mean, the difference between what I wrote here would be that you have to add a nonlinearity here. We're not going to do that today. I'm just going to do the linear case. Okay? And I think Tommy. I'm not sure Sasha, but Tommy for sure might mention related thing at some point in the class. Okay, so this is again, it's just a pointer. Okay, to create enough anticipation. Yeah. Let's take one thing at a time. Okay, let's take that's the question. the question is why we had the regularization, and for now we just throw it on your head, and so partially that's also why we want to do this discussion we want to do now. Why did we have regularization in the least square case? Well, we did it in a bunch of different ways. One way was because we had the linear algebra point of view, we had the shrinkage point of view. Let's see how that goes in this setting, okay? And so to do that, it's interesting to, useful to introduce the following problem. I'll call it V hat dagger, the following thing. So you take yi w transpose xi, okay? The product of a vector w, the function value corresponding to it, and the yi, okay? This is the measure of how correct is your solution, okay? And assume for a minute that for all I, you can find the w such that this becomes strictly bigger than 0, okay? So the data, it means that the data are separable. So this is an assumption. It exists w in Rd such that for all I, okay, there is a line that separates. So we're not looking at a non-separable case for now, okay? Then, if you, among many possible lines, a reasonable idea is to try to find one that makes this as big as possible, okay? Which means that in some sense you're far away from all possible value. You want this value to be as big as possible, right? Because it means that in some sense not only you are correct, you have the positive sign, but you are somewhat confident of being correct. That makes sense? So let's try to define a problem that makes sense of this request. So the idea is that you can look at the minimum of this guy, so the most unlucky point, okay? Fix a line and go check the closest point. And then try to find the line, w, that makes this quantity large. Is that clear? Yep. Yes. Because I'm pulling out the solution, okay? Yes. Which approximation? So, no, you can just think. In some sense, the idea here is, I don't do too much details here, but essentially the idea is when the product is negative, there is a mistake. When the product is positive, it's correct. If the product is very far away from being negative, you have confidence of being correct. If you're very close to be negative, you have less confidence to be correct. That's it, okay? So you go and say, pick a line, pick the point which make you less confident to be correct, and then try among all the lines to try to find the one that make it larger, okay? That makes sense? So this is a joint is a max mean minimization problem over possible w's. Okay? Is this clear? Now, this problem, as I wrote it, it doesn't quite make sense. Why? There is kind of I can trivialize it if I don't add some constraint. I'm just trying to make this thing big, right? Can you imagine a trivial way to make it big? Add a 3 gazillion here, okay? You can just scale things up. If you don't add something about the size of this vector, you can make the problem trivial. So the typical way of doing things is that you actually add the constraint and you say, okay, let me consider the case where w is norm 1, okay? And you remember at some point somebody asked, why do you take the minimal norm solution with the Euclidean norm of the interpolating solution? I said, well, it's just 1 is the most classical one. You can ask the same comment here. Why do I put this norm here? Just because it's the classical one, okay? And you can take the 1 norm, the 2 norm, the blah blah norm is a constraint. All it does is that it fixes the size of this from going to infinity. And it's the classical one. It has some nice interpretation that we're not going to discuss. For now, just it's a way to make now this problem meaningful. Is it okay? Now, we want to make a couple of, there are a couple of observations we want to make. So the first one is that there is a result that says that if clearly this problem makes sense only if this assumption is true. So we're assuming that this is true, okay? And then we have the following result that says that the limit of the solution of this penalized problem when lambda goes to 0 converges to this solution, okay? There is some condition on the loss functions that it makes this true. And let's say that I say that this is true for the SVM and from the hinge to the two loss functions that are written there, for the logistic and the hinge. The results is more general. But for this discussion, let's just pick those two examples. And let's see what this means. This means that if lambda goes to 0, not necessarily the solution, but the normalized solution is going to go in the right direction, which is this one. Okay? At this point, the proof of this is not one line. Okay? In some cases, for the logistic, you can kind of see an intuitive explanation. For the hinge loss is a bit trickier, so we actually don't want to comment on the proof of this. We just want to try to understand what it means. Okay? And what it means is that in the limit of lambda going to 0, the solution indeed has some kind of limit solution, which is not quite a minimal norm solution, but is the max margin solution. Okay? This is what you can call the max margin problem and corresponding solution. In this view, we can ask the question of why would I go this way rather than this? Well, the idea here is it obvious that you always want to do this? Well, if you have exactly separable data, or you really believe that your data are not that noisy, sure, that might be the best thing to do. But if you actually believe that maybe the data are somewhat noisy, okay, or they're even not linearly separable, then you have to account for the trade-off between 0 errors and the simplicity of your solution, okay? And that's what you're doing by, rather than taking the limit of lambda going to 0, rather than doing this hard margin-like problem, going back to a relaxed version of that, okay? So the idea is that rather than keeping this, you actually keeping this with the exact constraint, you relax this and you allow this solution. When lambda is different from 0, it's not true that you're going to find a separating solution. If you make lambda extremely big, at some point you're going to pay, and the error you obtain might be big, okay? And so you now have, again, a tension between a small error and simple solution. It has nothing to do with eigenvalues and pseudo-inverse. There is not the linear algebra point of view, but in some sense, this kind of phenomenon, the idea of going away from perfectly believing the data, potentially going to trade off between we want to at the same time believe the data, but find something simple, we just find it in the exact same way. Okay? Yep.
So how is this result working regardless of n?
No. This result is for those two loss functions as we are stating it here. So my statement is, if you take this loss function or this one, and you assume the data to be separable, then you have this result. Okay? The actual result gives you sufficient condition on the loss for this to be true, and then there are more recent results that give you necessary condition, and it roughly has to deal with the idea that the loss function kind of have to have this shape. So it has to go down, okay, with a certain speed. It cannot go down too slow. That's the basic idea on the assumption on the loss. But again, the proof is, well, at least for me, I didn't digest it enough to try to emphasize what are the main idea without blowing in just a bunch of computations. Okay, so this is observation 1 that we are where we give out, and this is the first answer to the question: why do we want to regularize in this case? Because maybe perfect separation is not what we can do or what we want to do, and then we want to somewhat find a balance between separation and simplicity of the solution. Okay. This parallel, I think this really gives you somewhat a parallel between minimal norm solution, Tikhonov or penalized DRM, max margin, penalized DRM. Okay. Yes.
Have actually a separate Tikhonov space and
So if the data are separable, you agree that this is what you want to do. This says, among all the possible ways to separate, pick the one that separates with, more space between the two classes. This is what this does by definition, okay? This one now you're trying to projecting something, but I'm telling you that there is a theorem that this gives you this in the limit lambda going to 0. Now you can ask what happens when lambda is different from 0. When lambda is different from 0, one way to think about it is, I don't make the request of making this small in the same way. If lambda is close to 0, I'm asking 0 error on my data. But if lambda is very large, I'm just asking for something simple, and I might actually allow error in the data. So if I want to allow error in the data, or if I have to allow error in the data because there is error in the data, I have to play the game at this level. If I want to go for the maximum separating, this lemma tells me pick lambda arbitrarily small, and you'll be in a good shape. Okay? The last small remark I wanted to add here is that, and you see perhaps here, at some point, the fact that you have this homogeneity property I mentioned enters the picture, right? I had to put essentially this constraint exactly because this can just go up and down, okay? The other observation I want to make is simply that another result is the following. Define now W hat dagger to be argmin of W in RD among all the W that satisfy the following. For all I W transpose I bigger or equal than 1, okay? So define a feasible set to be all the value that not only separate the data, but they separate the data with the one margin, okay, with some corridor. Then it turns out that you can now define a problem which is among all the possible solutions, try to find one with minimal norm, okay? Now, the two observations are, one, it'll really start to look very similar to the minimal interpolating solution. The only difference is that rather than asking here to interpolate the data, we want an inequality, okay? We want the sign of my W transpose X to be correct, rather than having W transpose Xi equal Yi. We just want the product to be positive. This is what is called the hard margin supervector machine, okay? And it turns out that if you take, of course, this solution in general doesn't have to be normalized, but if you do normalize it, it's the same as this. So if you take the solution and normalize it by his norm, you get the same as this. And this is now a standard, this is a standard fact from the theory supervector machines, okay? Max margin or min norm is completely equivalent, okay? This fact is standard, and this one is actually easy to prove. You just have to change variables a couple of times. Is an exercise. And if you want, it draws an even stronger parallel to what we discussed for least squares, okay? For least squares, we took this with least squares. We set lambda equal to 0, and we're converging to a problem of this form with equality. Xi W transpose equal Yi. Here we convert to something where we have the inequality constraint. Okay? All right, so again, this is just a small introduction to the idea of using this loss function that depend on the product. They are typically called surrogate loss function or large margin or margin loss functions, okay? And somewhat justifying in a way similar to the one we did for least squares, the idea of aggregating a regularization, okay? Essentially, the idea here is that, again, I'll say one last time and then I don't repeat it anymore. Interpolation minimal norm, relax that, looking at the Tikhon of regularization. You allow mistakes and you try to achieve some better stability. Here, the stability aspect is, at least in this formulation, less prominent. But the idea is that you want to find the max margin separation, okay, or the min norm separation. They're the same. And doing this in the limit lambda goes to 0 goes exactly there. But if you cannot or you don't want to separate the data, then you don't have to let lambda equal to 0, and you have to choose it some way. How? Cross-validation, because you have other better options. Okay? Any questions? Yep.
Saying that like the data is not separable,
Yep.
you still let lambda equal 0 because it converts everything equal in that case.
I don't think so. No, I don't think so. I think the question is, when lambda goes to 0 and the data are not separable, does it convert to something meaningful? I think it does convert to something. It's probably converts to something that does a certain amount of mistakes. But on top of my head, I don't know of any result that somewhat pinpoint what the exact meaning of that solution compared to something else. Other questions?
What is cross-validation in few words?
No, not allowed. Not allowed. Not in the advanced course that you have to take only if you've taken a machine learning course before, or if you know what machine learning is. I'm just kidding. Yes, I'm just joking. There are a bunch of flavors, but the basic flavor is take the data, split them in two, do that thing on half of the data, okay? And then choose, you find many solutions. So you have data set 1, you compute many solutions with different lambdas, and then you have to pick the solution you want. You try them all on this second half of the data set, and you pick the one with smallest error. And then, okay, this is the basic idea. That's the most basic. This is what is called holdout cross-validation, okay? Now, there are a bunch of, things like, why do I split in 2? How many times I split? Shall I split in 5? Shall I do 70-30? Shall I do 50-50? Shall I, once I pick the best lambda, retrain on the whole thing? That one maybe is the part that we don't want to discuss now. Largely because I have no idea what's the answer. It's more like, okay. But that's the basic idea. Split the data, train on half for different values of your models, and then pick the best model on the other half. That's the basic idea. Okay. Other questions? All right, so at this point, what we want to do instead is to take this and compute the solution. We're going to do it for logistic, and we're going to do it for SVM. For logistic, it's relatively simple. So let's make a couple of observations. For both, before we actually try to compute a minimizer, okay, let's ask if there is a minimizer. For both those cases, which is what we're going to study, this is a convex function of the W's. And in both cases, it's continuous. In the first case, it's differentiable. In the second case, it's not. The second term is always continuous, convex, and differentiable. Okay? Not only it's convex, it's strongly convex, meaning that it's a smile with no flat regions. Okay? And when you add a strongly convex something to a convex something, the sum is strongly convex. Why do we care? Because basically, a sum of all these assumptions, a minimizer of this exists, and not only exists, is unique. Okay? So now we can talk about this guy. There are not many, there is really one. Okay? How do you compute it? Well, how do you compute it is going to depend on the loss function. And by the way, I gave you the statement that this is minimizer exists and is unique for those two loss functions. You can kind of imagine for which other loss function you can make a similar statement. Least squares, sure. Exponential loss, sure. Anything which is convex and continuous, in effect you need a little bit less, will be fine. Yep.
So how do we know that the loss term is convex? Do we have to choose a convex loss?
Yes. Again, for today, that's exactly the comment I was making now. I only discuss logistic and hinge. But as you just did, you can imagine when the uniqueness holds anyway, which is when it's just convex. Okay, so that's true for any convex point. We want to now ask, okay, what about logistic? This is the case where we are dealing with this. Okay. This is the function we want to minimize. What do you do to minimize this? Well, it's convex differentiable. Let's take the gradient and let's see how it looks. Okay. In the least squares, it was the end of it because you take the gradient. You had the square here. You had a square there. The square goes away, and you got the linear equation, and you have to deal with a linear system. Even before we start the computation, do we feel like we're going to get the same result here? Of course not, because this is quadratic, and yes, we're going to have something linear, but this is a logarithm, so it's going to give some kind of nonlinear dependence on w. So we're not going to get a linear equation, okay? I'm going to compute the gradient just because it's going to be useful in a minute, but clearly we're not going to get a linear equation that we can just solve by, say, linear algebra tricks, okay? So we get 1 or minus e to the minus y w transpose xi. Then we got the minus yi xi, and then 1 e to the minus y transpose xi. So we use chain rule and some rule for derivatives. And we get this, okay? This is the gradient of this function on top, if I didn't make mistakes. Now you could say, okay, I put it equal to 0. You find out that that w will be equal to this kind of stuff, but you see that the w also appears here. So it's going to get a bit more complicated, okay? It's not crucial, but also let me simplify this expression a bit. Divide both the numerator and the denominator by e to the this same exponential here. What you get? You get the 1, you get the 1, and then you get 1 over the exponential, which is just the exponential without the minus. Okay? So if you allow me, I'll just cheat and do this. Okay? Just because I can write less, which is always important. So how do you solve this problem?
Numerically or
Yeah, numerically, with the computer. Gradient descent seems to be a good candidate, right? Of course, now you want to use SGD and this and that, but that's the simplest possible idea is just gradient descent. What is gradient descent? Well, we have to take Wt plus 1 equal Wt minus a step size. I'm going to call it gamma, yes. And then I have to take the gradient at the tth iteration. So I'll put here t, put t, and I'm done. Okay? How do you choose the step size? You remember in this case? How do you choose the step size of any gradient method you know? Do you know any? Have you ever used the gradient method? No, but that is actually, I think it's actually a very good answer. But somebody else taught you another answer. This is the good answer. This is the right answer. But what is the one that somebody else taught you? Right, that's complicated. So you can do line search or backtracking. There is one Hessian, but we take that one. Is the smallest eigenvalue of the Hessian, okay? And why is that? Do you have an intuition of how you choose that? Right, but yeah, exactly. So the rough idea in this picture is just you have this thing here, you want to go down, okay? You're going to go down the direction opposite to the gradient. And then what's going to happen is that if your function is very sharp, you have to be really careful to make small steps around the origin, otherwise you keep on jumping back and forth. If your function is super duper flat, then you can take big jumps, okay? Flatness is second derivative. Second derivative would be Newton method. In one dimension, that's okay, but in multiple dimension is computing the Hessian. And you don't want to compute an Hessian at the iteration, at every iteration, so you just try to find an upper bound, okay? And in this case, it's all nice because everything is smooth, and so you can actually take a constant step size, okay? What is the constant step size? Is exactly a bound on the norm of essentially the smallest eigenvalue of the Hessian, okay? This, I assume that either you know, you can pick it up quickly, and it's pretty standard, so I don't want to discuss that further. Just, the key point is that you have this standard thing, and then you can put here a constant step size, okay? That's something to remember. Okay? What is the computational cost of this? It's not bad, because at every iteration, you just do a matrix vector multiplication, okay? Here, that's the main cost. How much is the cost of this? This is long D, this is long D, this is going to cost you D. How many times you have to do it? N. So this is going to cost ND, and then you have to do it for as many times as you do iterations. Okay? And of course, if you repeat this operation for multiple lambdas, you also have to factor that in. You have to recompute this again and again. Okay? So not bad. And this stuff turns out to be state-of-the-art in large-scale modern machine learning, not because people working in numerical analysis and optimization are kind of sad about this, because they've been working on saying that this is horrible for ages and trying to do Newton, quasi-Newton, and this and that. And it turns out that when you have really huge x and y's, this is kind of what you can afford. A and B, these operations are really easy to parallelize because it's just matrix vector multiplication. So it's kind of easy to use. And so the question is not anymore if you can do something different from first-order method, but what are the best first-order method. And we're not going to discuss today, but the possibility is essentially remove this and just do stochastic gradient. You took each step, you just take 1 point, and you take a step in the direction of the gradient of the loss on that point. Or you can say, what about a few points, a mini batch? Okay, you divide your data in groups and you do that. Okay, and that's not what we want to discuss now, and we might touch upon this when we talk about stochastic gradients, but I'm not sure. So this is all we want to do. I imagine so far so good. Okay. Now, do you remember how we went from linear to nonlinear in the case of least squares? Also, okay, first of all, before we even go. Yeah, let's go nonlinear in a couple of different ways. We went nonlinear either using feature maps or using kernels. What was the story for feature maps? If the feature map is finite dimensional, it's just a bunch of features, what do we do? Every time you see x, or you call it phi of x, okay? This is a vector in Rp, and it's all the same, just all the same, okay? Just every time you have x, replace it by xi, by phi of x, and every time xi, phi xi, and so on and so forth. It's the same, okay? Of course, when you talk about, say, the Hessian, okay, it's not going to be Hessian of the data set, but the data set in the feature space. So you have to do things right, but you just, you have to do this right, but you don't have to do anything smarter than that, okay? What about going to kernels? Do you remember how we did it? We discovered that the W we were looking for was not just any W, but was a W of this form. Or equivalently, that the corresponding function could be written this way. Ci are numbers, xi are vectors. The vector is a linear combination of the input points, which means that the predictor is a linear combination of inner products with specific coefficients. And the coefficient in the case of least squares were the solution of another linear system. Okay? What we want to prove now is that we can do the same thing for this iteration. And we're going to derive a representation for this iteration of this form. Okay? So the plan, more precisely, is to show that for every t, Wt that comes out of this procedure is of this form, and I'll put it here because I don't know where to put it, for a specific CIT. And I'm going to tell you, or hopefully you're going to tell me, what is we're going to be precise about how the CT are generated, okay? Which means that the corresponding function, okay, is also going to be satisfying something like this. So that's our goal. We want to show that this Wt satisfies these two equations and provide an expression for the CTI. Is that okay? How do we do it? We can do it by induction, okay? The base case is very easy. So what we want to do is that let's assume that this is true and prove it for WT plus 1. Is that okay? Before I start to do stuff, is the question and the hint of how to prove it clear? Is anybody alive? Good. So, I guess the most important thing to do is to put here this xi here, okay? It's a joke. This is stupid, but the proof is not very hard, okay? So, I like stuff which is a combination of xi something. So I put this in that form, okay? This is something. Then I assume, okay, before I start to delete, I'm going to delete, sorry, I put this in the wrong place. I'm going to put this WT and put this expression because that's the inductive hypothesis. And then I see what happens, okay? That's what's going to happen right now. And I also have to do it here. I have to do it here. Yes? This is I'm doing it for the gradient. I'm showing that the W that comes out of the gradient iteration is of that form. The reason why I'm doing this is because I'm going to tell you not only that it is of this form, but I'm going to give you an evolution equation for the coefficients. So that's what I'm doing right now. Okay? I also have used the inductive hypothesis here, right? Which would just give me this, if you wish, okay? Where Txi satisfies this expression. Well, I have to do it here too. And now I argue we're done. We're finished. Do you agree? There is xi CIT. There is xi. This 1 over n doesn't matter. You can just pull it in. This is xi times a coefficient. And there is xi times some other coefficient in there. So I can actually rewrite this as wt plus 1 equal sum of I from 1 to n xi t plus 1, where c, let me see what is the best way of writing this. So literally what you have to do here is that you have to factorize this sum over xi everywhere, okay? You have it here, you have it here, you have it here. So you can factorize it out. And then you have to check what's left. What's left is this. There is a CT coming out of here. There is a CT hidden here, and there is another CT there. Which means that the solution can indeed be written as a linear combination of the input points, where CT plus 1 satisfies this recursion. What is this is just the orthonormal basis in Rn. So you update each coordinate separately. Okay, that's what this says. Okay? There's not much else going on. Okay? So this computation you have to do it yourself once and I'm skipping the one passage where the intermediate step between this and this, but there's nothing else. Okay? And this shows not only that the gradient descent for logistic regression satisfies one of these this property, but it also tells you how to compute the CI through this. Okay? And this is the right way of doing it. Notice that here there is only the coefficients, and here in this expression you have to use the inner product. Okay? Because ftx is equal to that. If you now replace the inner product with a kernel, you're good to go. Okay? Yep. It just, instead of doing this, you can now write down the equation for each the components. Okay? So the component, this is just a way to write down in a compact way. You can see it from here, essentially. This is a number, okay? And this has to be associated for the first example. So this is the way you update the first coefficient in the C's, okay? So here I'm just writing the compact thing for all of them. This is the way you update the first component of the first vector, and this is just one way to write that down. Sorry? This is one way to, that's exactly what I'm saying. This is one way to do it. This is a vector that contains all, when you take I equal to 1, it's going to contain a vector which is all 0, say but the first entry, which is going to be equal to this. And that's how you update the first, the first element. Then you take I equal to 2, you're going to take the vector is 0, 1, 0, 0, 0. You multiply the 1 by this, and this is how you update the second component. Okay?
Or we could just put J everywhere.
You can put J everywhere. It's the same. Exactly. You can just put here. I just that I had too many J's. You can put a J here, and then it's the same thing. Yep.
So is doing it this way faster than gradient descent?
No, it's the same. So what we gain here is that now we can do kernels. So the whole game, we're doing what we did here is this. Okay. Now we can do kernels. Okay. That's why you do it. So now you can use this and do kernelized regularized logistic regression with gradient descent. Okay. So that's what you want to do. Just show how you do it. And the reason why we really do it in this class is because this is how we're going to do SVMs. Okay? So that's why we want to do it like this, because the first thing is standard, the second thing is simple, and then we're going to do SVM in the exact same way, and we're going to do SVMs in the primal, which is what people really do these days. Okay? Just as a small remark how this relate to what you might have seen before, okay? If you have seen, say, logistic regression with kernels before, what you typically do is that you prove a representer theorem for the solution of this problem, and then you take the gradient descent of this. We're not doing that. We're taking a representer theorem for the iteration. One of the exercise, spoiler, that you're going to get today is going to be to prove a representer theorem here, to do the gradient descent on this expression with the representer theorem and compare it to what we've done in class. And you'll find out that this is better. You have an extra, one less matrix multiplication to do. Okay? Okay. So the idea, this is just the kind of computation you have to do. What about supervector machines? Supervector machines are this thing here. Okay. The problem is again convex, strongly convex, in fact, because we add at least for any lambda bigger than 0, but it's not differentiable anymore. So what we need to go on is one idea, one definition. And then we have to know how to compute left derivatives. So we're gonna, if you have seen SVM before, typically you introduce SVM, then there is margin this, margin that for a while, and then at some point you talk about Wolf duality, Karush-Kuhn-Tucker condition, quadratic programming, okay? The whole idea is that we're gonna replace all that by left derivatives, okay? Which is, because presumably this is a slightly more friendly notion. To do that, I'm cheating a bit because we do have to introduce a more sophisticated idea, but hopefully it's more intuitive than Karush-Kuhn-Tucker condition and duality. We just hide it, okay? It's still there, but we hide it. That's the basic idea. So suppose that I give you this function, for example, okay? It's quite nice, almost everywhere, but in this point, you cannot take derivatives. What can you do? You can take left and right derivatives. Because it's continuous, it's convex, so left and right derivatives are going to be well defined. So in a nutshell, in the simplest case, what is a subgradient? How many of you know what a subgradient is? Okay, in the simplest possible case, a subgradient is not one number, like the derivative, but it's an interval. The interval between the left and right derivative, okay? So here, you'll be able to, in this point, let's call it W0, you can get, f minus W0 and f plus W0, the left and right derivative. Go to any other point, you get one number, okay? So if the function is differentiable, the interval become a number and it's just the derivative. If the function is not differentiable, what it was a number, like spread out into a bunch of numbers. The notation you use is this one here. This is the main intuition, okay? This is the main intuition of why you use this. Yep.
What's the left right derivative? Is that just like the squares, like the left side?
Yeah. It's the high school left and right derivative. Yeah, that's it. It's the one that I'm doing things for one-dimensional function, okay? In one dimension, you take left and right, okay? Is that okay? Now, if you go in more than one dimension, it's trickier, so you cannot do just left and right derivatives. So you have to have a more general definition. And the idea is that the more general definition essentially is the one that says that delta f W0. So this is the definition for W in RD with D equal to 1, okay? That's good enough. When I want to do the definition for a generic D, and here is the 1. This is the set of vectors, how do we call it? V such that for every W, so in RD, you have the following thing. Okay? Now, if rather than thinking about it, you draw it in the one-dimensional case, this essentially means that if you take any, is the geometric fact that if you take any of this derivative, it essentially gives you one of the possible lines that lie below the function, because it's convex, okay? So if you wish in more than one dimension, that's the idea. If you have a pointy thing, okay, you take all the possible derivatives, okay, which are going to be all the possible linear curves that touch the thing in the W0 point and lie below it, okay? So I hope it's quite intuitive, okay? So this is going to replace duality for us, okay? Is that okay? Yes. That's a good question. The question is, if I have an interval, which one do I choose? Okay, and the answer to derive the algorithm is going to be the left derivative. And you can ask why, and I say why not? Okay, and you can say, what about another one? Well, which one would you want to choose? The right derivative? That's the same. You want to choose another one, then it becomes a problem. You have to show that there is a good one. Okay, we'll see that there is indeed an amount of freedom in choosing which one we want, and we are going to choose one. and we're going to pay a price. And the price is going to be that this step size will not be chosen constant anymore, okay? This is going to be the basic subgradient algorithm in one instance where you can easily compute it. And we choose, say, the left derivative because it's easy, 1. And 2, because once you write it down, it's one step away to make a connection with the perceptron, okay? Which is a classical algorithm, okay? Is that okay? So this is the definition in case dimension 1, and we are going to use this one to make computations. And then this is the definition in dimension bigger than 1, and we have a couple of observations. The first one is that we have a sum rule. If you have a sum of convex function, you can compute the subgradient as the sum of the subgradient under some under some assumptions that are satisfied here with some finiteness assumption. And then you also have the chain rule. So you have the composition rule. These are the two things when I said sum rule and chain rule was not to show that I remember what they are in the one-dimensional case, but to point out that that's what we use there because we're going to use it here, okay? And the last thing we have is that if you now want to minimize, so if you want now to minimize a function in Rd, which is continuous and convex but not differentiable, just give me 1 second. You can now use, rather than the gradient, the subgradient, which is just this. So if I want to minimize a function and the function is not differentiable but is convex, I do run an iteration where it's this. There are two differences with respect to the gradient descent. The main one is that rather than the gradient, we have to use an element of the subgradient. And you're back to the question which one you select. But this gives you the freedom to select one, okay? And then the big difference is that the step size is a constant, which is pretty much the same as the one before, but divided by square root of t. Okay? These are the only two differences. This is not a descent method, and that's why one of the reasons why you need this. That algorithm ensures to decrease the value of the objective function at each step. This one is not, and you kind of have to be sure that you actually make it go down somehow. So that's the reason why you add this decaying term. Yes?
In the definition of a subgradient, is there a constraint on V? Because we could have one going in a certain direction and just keep shrinking it, and that would still satisfy the definition, right?
Yeah, it's fine. Any direction which is there is fine.
We can have the same direction, but
Yeah, and you're going to count it more than one. Yeah. Yep. No, and it is just, and I'm just mentioning one of the results. The question is, so the first question was, there is a certain degeneracy in the way we define subgradients. Yes, there is. It's a big set, and for now, that's the main thing. If you go back to differentiable, every become just one, and you can play the same game. Okay. The other thing is y square root of t, and I write there just one basic result. Okay. Under a different assumption, you might be able to get slightly different step size, slightly different rates. You can consider the one thing that often people do is to consider the average rather than the last iterate or the best, the last iterate. That's just one very basic formulation, okay? And I'm not even writing the value of the constant explicitly because this is somewhat, I think I have it in the notes and in the slides, but this is not like the key point of this discussion, okay? Qualitatively, the important bit is that it's not constant, okay? Now, exactly how it has to decay, it's not the main point. Okay, so that's the 6 minutes introduction to convex optimization and convex analysis. Okay, based again purely on the data that there is a notion of derivative for a convex function which are not differentiable. The nice thing is that in the one-dimensional case, it just becomes the integral between the left and right derivative. I can use I have an analogous of sum and chain rule, and I have an analogous of gradient descent. which is not a descent method, but is the subgradient method, where I have to select an element of the subgradient and then pick a decaying step size. Okay? What do we do now? We use it. We just use it. Okay? We put it here and we use it. And what do we get? Well, the same as what we had before. And how do we get from linear to nonlinear? The same way we go before. And how do we go from features to kernels? The same way we go before. So this was, you know, the biggest effort in this whole class, presumably, is digesting that information and now using it, because the rest is just a summary of things you've seen before. Was a question? Question? No. All right, so let me just take the exact formulation I use here, so they use the same symbols. Okay, so I'll write this for our problem. Start to think what you think is the subgradient of this function, okay? While I write. So our function, the loss function, is 1 minus a positive part, okay? Which means that the function looks like this. What is the left and right derivative of this? Well, it depends if I'm here or here, okay? If I'm specializing this point, it's an interval between -1 and 0, okay? In what we do, A is going to become yi w transpose xi. And we have to check if that's smaller or bigger than 1. Okay? If it's smaller than 1, we get -1. But then we also have to do the chain rule. So this is, we have to put here y w transpose xi, y I w transpose xi, and take the derivative with respect to wi. What's going to be? The derivative with respect to this is easy. It's just yi xi. The derivative with respect to this is either -1 or 0. Okay? So we use chain rule to compute the gradient of each element in the sum that defines the empirical error. And then we use sum rule to just compute the whole empirical error. So the sum we already used here. Now I have to write down what it is. Can you tell me what it is? This is the subgradient obtained taking the left derivative. And now you see I could take the other one, but if I want to go in the middle, it's tricky. What is going to be?
YIWT is greater than 1.
Is what, sorry?
It's 0 when YIWT is greater than 1.
Mm-hmm.
And it's negative WI XI.
Very good. You agree? And what if it's 0? Well, now you have to make the choice, left or right. I'll take right. I don't know. I'll pick this one at random. I don't care. Okay? Boom, that's the algorithm. Okay?
But we didn't use the concept of the interval. I mean, it shows one of the elements.
We have to, so what he's saying is that we didn't use it. Well, kind of, because what we did is that we know that there is a whole interval. And we know that this algorithm depends on the selection of one of the elements, and we just pick one convenient choice. And here was the left. If you want, this is the left derivative of this function, okay? So this thing here is essentially L minus y W transpose xi, yi W transpose, okay? That's what this is. The left derivative of this multiplied by what we get by chain rule. Is that okay? So it's simple. This is what you do when you do SVM in the primal. Okay? So it used to be the case that one usually use this quadratic programming formulation, but now if you have very big data, working in this way and just doing subgradient is convenient. And of course, at this point, you can ask yourself, well, can I make this faster, and so on and so forth. Okay? This is just a basic solution. Yep.
Practically, are we ever going to get to mono? So this concept, we're at that point, the whole notion of what is the derivative of that on that point relies on that we have to have that exactly equal to 1.
Mm-hmm.
And is that something that happens in practice?
Well, so the question is how much we have to worry about the 1 and the fact that we get that point in practice. Well, if you wish, there are a couple of point of views you can take here. Okay, one is if the function is not differentiable, what the hell am I doing? Okay, is there any results I can advocate to say that this thing that I'm doing works? And you cannot just say, what if I have a function which is kind of differentiable but not really everywhere in some places? That's an argument which is harder to make. So this makes why this works. We have a guarantee that this works. Okay. Now, from a practical point of view, if you want this, just say the heck I do when I take left derivative, it's fine. Okay. So just as confirmation, that's okay. There are other formulations that I'm not sure if I have time to discuss today because we're kind of late, but you find them in the notes that shows that you can actually exploit that one point to try to get sparse solution. And that's the main reason to use things the old way, the super vectors old story. Because if you see here, one thing which is still outstanding is why would you call this thing support vectors? Okay, it's not clear at all. So one can actually show that you can use the presence of that to actually get that sparsity. Yes? Yeah.
So, in Prof, at each step we have to compute the TLB style, which needs m.
It's the same. So yeah. So let me do it. So the question is, how do you compare the cost of that? Maybe you can all think a second about it. How do you compare them? So you have to do iterations in both cases, and the main cost is at some point doing a vector-vector multiplication that you have to do n times. Okay. So if you have to compute this, okay, this is going to cost you d. Because there is this thing here. You have to check whether it's bigger or smaller than 1, and this is going to cost you d. Because you have to multiply this and this, correct? Well, then I haven't read. It's? Yeah, but you still have to compute this. This is the main cost. Yeah. It's the same. So we haven't, let's write it here. We haven't read, if you want, let's take a step back. What is the computational cost for kernels here? Maybe let's write this first, because then we haven't even derived this word. So
My point is that it's like m squared.
yeah, let's do it. It's n square t, okay? Plus the cost of computing the kernel. That's what you have to do, okay? And here is the same. It's just that I haven't written yet, so maybe it's not super easy to see.
It's empty because why? You don't have to compute it.
Well, because there are no kernels. When W is going to become of this form, here you're going to have an inner product, and you're going to have exactly the same thing. Okay. But maybe we do it, and then... in fact, maybe I was thinking... maybe I don't do it, so... where is it? So essentially the preparation to answer the question is, this is the W version of the algorithm. Can I do a C version of the algorithm? Can I represent WT this way and do the same kind of trick? The answer is yes. Okay. How do you prove it? In the exact same way as before. So you just proceed by induction, okay? You assume that the base case is easy. You assume it's true for WT. You take this WT. What did we do there? We just plug this WT in here, and in here, and then we just see that we can factorize everything out, okay? I would like to skip this because we don't have enough time, and I'll try to show you something else instead. But just to give you a feeling, if you want to try to do it, that it's clearly the same thing. WT is going to have the xi by assumption, and the t by assumption, the inductive hypothesis. Same here. Hidden in this si, there is an xi. Hidden in this si, there is an xi. So in some sense, you have to factorize it out. And then you can do the same thing. Maybe what I do is instead write down the...
This is even nicer than the previous one, I think. Because it's all WTXI. There's no exponent.
Yeah, but it's kind of, so the comment is about the fact that here there is not the one exponent, it's just a product, yes. The coefficient is a bit simpler. So, So it looks very similar to this. The main difference is, again, the step size, and then the fact that I have to compute that gradient. And this gradient essentially is a representation of that subgradient where I pull out the xi. So you see here I have an xi. Here I'm just updating the corresponding component, and I put the element of the basis there, the same trick I used before. And here, to actually compute the constraint, I have to compute not yi w transpose xi, but yi ft xi, where ft xi is equal to this. So now I have a kernel. Okay, I teach that. And now we can go back to your question. What is the cost of this? Is the same exact of doing that. Okay, how many times you have to do it? Well, if you do a lot of correctly classified points, less times. You might not have to do it for all of them, but you still have to check. So you don't have to do all the updates, but you still have to check whether it's correct or not. So in the end, it's going to be n squared t in exact same way. Okay? All right. So I'm running out of time. So let me just wrap up and tell you what I didn't talk about. Okay? This is pretty much really what I wanted to talk about, the main thing I wanted to talk about today. And this is our treatment of SVM, which is really somewhat uncanonical, or maybe not traditional one, but it's kind of the more modern one, okay, with some details like the usage of certain tools from conflict optimization is replaced by this perspective. One of the things that I did not do much is to try to rederive the SVM through the whole margin formulation, but we kind of did it a bit at the beginning by studying this limit for lambda going to 0, okay? So we recovered a bit of that. The thing that I really didn't do at all, which is a bit of a pity, but you find it in the notes, and maybe we can discuss it offline who's interested or during office hours, is giving right to the name supervector machines, okay? Because this is something that you might want to call regularized hinge loss with subgradient, okay? Let me just add one word about this. You know that when you have to study the minimum of a function, you take the gradient and set it equal to 0 if it's differentiable, and that's this first order optimality condition. There is an analogous of this in terms of subgradient. If the 0 is contained in the subgradient, then that point is a minimizer. You need to have a point where the lines go from like this to like that. Intuitively, that kind of makes sense. Clearly, at that point, it's not going to be an equality, it's going to be an inclusion. You need to have, you have to be within the left and right derivatives. In a nutshell, this is what gives you the box constraint for an SVM. Okay, so if you have seen SVM before, you know that at some point you get that they look like this with some coefficient that satisfies Kuhn-Tucker condition under some box constraint. The box constraints are nothing else that assuming that there is a zero in the subgradient. So again, it's a totally elementary computation. I rechecked this morning, so hopefully it's correct in the slides, and you can just check it out yourself, and we can discuss offline. Okay. Okay. So this is for us, as I said, is just an excuse to do 2 pigeons with 1 stone, take out of the way 2 of the most famous algorithms around, logistic regression and SVM, but also see how we can use first-order methods to deal with them, and introduce how they are related to the notion of margin that will be useful later on. Okay.